black holes are at the center of galaxies, and those are typically gargantuan black holes, millions or billions of times the mass of the sun.
To discover the mysteries of the cosmos, physicists have historically relied on a variety of theories, including the Standard Model, quantum mechanics, and general relativity. These theories have been successful in providing an explanation for cosmic occurrences, illuminating the behavior of celestial bodies and the complex nature of particles at the tiniest scales. There would be a plethora of unresolved questions about the universe if theories weren't there to guide us. But what if all along we've been mistaken? At last, Brian Greene has come out to say that we are living within a black hole and that all current hypotheses are false. Come along as we unravel the mystery of what Brian Greene was discussing 0.4 billion years ago, rotating around each other, approaching the speed of light, colliding, and causing a tidal wave in the fabric of space, and consider how this finding might alter everything we have ever believed to be true about our reality. Few voices are as influential in the field of theoretical physics as Brian Greene's. His outstanding contributions to the subject, especially in the area of string theory, are irrefutable. He has become a significant figure in the scientific community due to his breadth of knowledge, coherence of ideas, and ability to explain complex ideas to both specialists and lay people. Greene's knowledge goes much beyond his outstanding findings and study. He has a remarkable gift for using his writings, talks, and media appearances to help solve the universe's puzzles. He has succeeded in bridging the gap between the curious public and the arcane realm of theoretical physics with his best-selling books like The Elegant Universe and The Fabric of the Cosmos. His exceptional talent at reducing intricate concepts to universally understandable stories has enabled a great number of individuals to interact with difficult scientific topics. Thus, he has also contributed to the expansion of the scientific community at large. However, Greene's professional achievements and educational background are what really establish his powerful standing. As a physics and mathematics professor at Columbia University, he has fostered a new generation of scientific minds by mentoring and inspiring many young scientists. His work in string theory, a framework that seeks to unite the fundamental forces of existence, has advanced the discipline and brought him international acclaim from peers and specialists. Therefore, the world pays attention to what a man like him says. Furthermore, he has suddenly declared that every contemporary theory that we had previously relied upon for explanations is false. We live inside a black hole as opposed to merely our solar system. We have been within a black hole the entire time, and everything we have been taught about our world is untrue. However, how is it possible? Could contemporary theories be so incorrect? In fact, scientists have been investigating the possibility that our universe may be contained within a black hole for some time now. A number of hypotheses and concepts have been put out over time to explain how our universe could be related to or descended from black holes. Some scientists have proposed that every black hole has the capacity to create a new universe. This idea is based on the theory of torsion, which postulates that a new universe is produced inside every black hole. This view holds that black holes serve as cosmic portals via which new universes are born. According to a different theory, the black hole that houses our observable world is a component of a bigger parent universe, or multiverse. According to this perspective, black holes act as portals to different areas or dimensions of spacetime, which include several worlds or universes. It is also thought that the singularity, or the endlessly dense center of a black hole, might be the place where new universes are created. There are specialists who propose that our cosmos could have originated from the singularity inside each black hole. This theory makes a connection between black hole singularities and the original condition of our cosmos, which is known as a singularity. The idea that a black hole within another universe is the source of our cosmos is another intriguing possibility. This hypothesis states that a white hole on the opposite side of a hypothetical wormhole concurrently gives birth to a parallel universe when a black hole arises as a result of the collapse of a dying star. This theory links the genesis of new universes to the production of black holes. Not only that, but some theories even suggest that our universe may be within a black hole with a higher dimension. According to this viewpoint, our cosmos originated as a singularity, a point of infinite density and temperature, much to how black holes are described by science. According to the theory, a four-dimensional black hole's event horizon contains our universe. This would imply that, despite our best efforts, we are unable to detect the fact that we are within a black hole. However, as you can see, this hypothesis contradicts all of the facts we have already researched and established about how our own universe functions. From the greatest structures to the tiniest constituents, the basic essence of the world is sought to be explained by a variety of theories within modern physics. These ideas, which have been created by thorough scientific research, have offered amazing insights into how the universe functions. The foundation of quantum mechanics, which explains how particles behave at the atomic and subatomic sizes, is the basis of contemporary physics. It presented an alternative path from the rigid principles and exact measurements of classical physics. Wave-particle duality is a fundamental idea in quantum physics that reveals the nature of the microscopic universe. It demonstrates how particles like electrons and photons may have characteristics of both waves and particles. This implies that in addition to exhibiting wave-like properties like interference and diffraction patterns, they may also behave as discrete particles with precisely defined locations and momenta. The mathematical description of quantum mechanics, which describes the probability distribution of finding a particle in various states using wave functions, captures this duality. Superposition is yet another amazing feature of quantum physics. This concept asserts that particles can exist in more than one state at the same time, which is not seen in traditional physics. An electron, for instance, can exist in both spin-up and spin-down states simultaneously until a measurement is taken, which collapses the wave function into one of the conceivable states. Then there is entanglement, which is yet another fascinating aspect of quantum mechanics. When two or more particles exhibit strong correlation, their states become interdependent despite being separated by great distances. Regardless of the physical distance between two particles, when they are entangled, measuring the state of one particle instantaneously determines the state of the other. This phenomena is being investigated for potential uses in quantum computation and communication after being verified experimentally. The power of quantum mechanics to precisely anticipate and explain a wide range of tiny occurrences is what makes it so successful. It offers a coherent framework that can explain how photons are emitted and absorbed, how electrons behave within atoms, and how particles interact within particle accelerators. This knowledge has aided in the creation of several quantum mechanically based technologies, including transistors, lasers, and nuclear power. Upon closer examination, quantum mechanics provides a microscopic understanding of the world we live in. These are the building elements of existence, and we have understood that everything operates in a specific manner, the way that reality is meant to be, ever since their discovery. That's not all, though. Numerous theories have long been employed to explain the nature of our planet and the workings of the actual world. One such theory is general relativity, which defines gravity as the curvature of spacetime brought about by matter and energy. It offers a mathematical foundation for comprehending the actions of huge objects, such as galaxies, planets, and stars. Numerous phenomena, like as the expansion of the cosmos, the precession of Mercury's orbit, and gravitational lensing of light, are satisfactorily explained by the theory. Even yet, there are extreme situations where general relativity fails, including at the core of black holes or in the first moments of the Big Bang, necessitating the development of a more comprehensive theory of gravity. However, particle physics standard model goes one step farther. This is a very effective theory that offers a thorough framework for comprehending the underlying particles and forces that comprise the cosmos. It includes the weak nuclear force, the strong nuclear force, and the electromagnetic force, three of the four fundamental forces. Every one of these is essential to the operation of our cosmos. Interactions between charged particles, such as electrons and protons, are caused by the electromagnetic force. Conversely, some nuclear reactions and radioactive decay are examples of processes that involve the weak nuclear force. Strong experimental evidence supporting the validity of the electroweak hypothesis has been supplied by the finding of the W and Z bosons, carriers of the weak force. Atomic nuclei are held together in the conventional model by the strong nuclear force. It is in charge of the interchange of gluons that occurs between quarks, the basic particles that comprise protons and neutrons, during their interactions. The strong force's behavior is described by quantum chromodynamics, a branch of the standard model that has undergone satisfactory experimental testing. Therefore, the theories we are discussing here are not just hypotheses, they are the reality, as evidenced by numerous instances of proof. Furthermore, the Higgs boson, a particle connected to the Higgs field, was also expected to exist under the Standard Model. It is believed that interactions between particles and the Higgs field are what give particles their mass. The Higgs boson's existence was verified in 2012 by experiments carried out at the Large Hadron Collider, adding even more support to the Standard Model. However, in spite of its achievements, the conventional model is not without flaws. Its inability to take into consideration the existence of dark matter and dark energy, which are thought to make up a sizable fraction of the universe, is one of its main limitations. It is deduced from dark matter's gravitational pull on visible matter that it is a kind of matter that is unaffected by light or other electromagnetic waves. On the other hand, the observed accelerated expansion of the cosmos is thought to be explained by dark energy. Comprehending the characteristics of dark matter and dark energy, which are essential components of black holes, is still a thriving field of scientific inquiry. But the difficulties don't end there. The attempt to integrate the gravitational force with the other basic forces presents another challenge. Gravity is not represented by the Standard Model, rather, it is described by the independent theory of general relativity. So perhaps Brian Greene is right after all. As you can see, his real area of specialty is investigating the essence of the cosmos, looking for a single theory that unifies all the forces and particles. Greene's work on the idea of mirror symmetry and superstring theory is one of his most important contributions. A deeper relationship between two seemingly different Calabi-Yau manifolds, higher dimensional geometrical spaces, is established by mirror symmetry. The surprising connections between what appeared to be disparate mathematical explanations of the cosmos were revealed by this finding, which completely changed our understanding of string theory. These little variations also allow for Greene's idea. Perhaps the distinctions, little as they may be, add up to something more than the realization that we are not alone in space. Perhaps all along we have been living within a black hole. But as you can see, things get much more fascinating at this point. The scientific community frequently discusses black holes for a reason. As more is discovered about this one topic, the mystery surrounding it only grows. As to prevailing beliefs, a black hole is an area in space where the gravitational pull is so powerful that nothing can escape it, not even light. This extraordinary property results from the extreme concentration of mass in a small region, which completely distorts space and time around it. The truth is that black holes have incredible characteristics that distinguish them from all other things in the cosmos. Their extreme density is one of their distinguishing characteristics. A black hole's mass is concentrated into a little area, creating a gravitational field with enormous strength. Since even particles traveling at the speed of light cannot overcome this gravitational pull, an event horizon, a limit beyond which nothing can return, forms. Black holes only have three characteristics, though, despite their enormous gravitational attraction: mass, spin, and electric charge. The main feature that distinguishes a black hole and ultimately determines its gravitational pull is mass. An object's spin, or its angular momentum, is what gives the black hole its name. These items rotate in an angular manner rather than in a clear-cut, uncomplicated manner. That explains why black holes can vary from one another as well. The entire black hole alters at even the smallest variations in their angular momentum. Although theoretical physicists have created a number of theories to explain many black hole varieties, stellar mass black holes are by far the most prevalent kind. They are the result of huge stars collapsing gravitationally at the conclusion of their life cycles. The mass of a stellar mass black hole usually varies from 3 to several hundred times that of our Sun. Their development is a result of a catastrophic event when a dying star's core collapses due to its own gravity, creating a compact object with a strong gravitational attraction. There are theoretically more kinds of black holes than stellar mass black holes, such as supermassive and primordial black holes. Most galaxies, including our own Milky Way, are thought to have supermassive black holes at their cores. Even though their mass is millions or even billions of times that of our Sun, scientists are still trying to figure out how exactly they formed. On the other hand, primordial black holes are speculative objects that could have developed soon after the Big Bang. Their mass might vary from microscopic to enormous, and they would have come from instabilities in the early cosmos. Though analyzing the more intricate black holes may be a little more challenging, scientists are nevertheless aggressively searching for and studying every black hole they can locate. Black holes may be found and studied using a range of techniques that astronomers use, which helps us understand more about these cosmic objects. One method is to measure the gravitational pull that black holes have on nearby stuff. The motion of stars and other bright objects provides astronomers with information on locations of extreme gravitational force. For example, stars have been discovered orbiting an apparently empty area at the heart of our Milky Way galaxy, which suggests the presence of a supermassive black hole. A further approach is to investigate stuff that is accreted into a black hole. An accretion disk, a structure made of gas and dust in the shape of a disk, is created when matter spirals into the black hole. Extreme heat is produced by the disk's friction and strong gravitational pull, which leads to the emission of X-rays and other wavelengths of light. This gives scientists important new information about the properties and actions of the black hole. Astronomers may even be able to see the dazzling emissions coming from matter falling into a black hole up close in certain instances. Matter travels at extraordinary speeds in the direction of the black hole, producing a great deal of heat and radiation. Scientists may analyze this radiation, which can be detected at many wavelengths ranging from visible light to X-rays, to get important insights into the characteristics and workings of black holes. However, this is not how all black hole research is done. Another way to find black holes is to observe how neighboring stars move. Astronomers can identify aberrant patterns or aberrations that indicate the existence of an incredibly large object by analyzing the exact motions of stars in the region of a suspected black hole. These findings improve our knowledge of the black hole's gravitational pull by offering important hints about its mass and position. An additional line of inquiry into black holes has been made possible by the discovery of gravitational waves. Massive objects accelerate and generate ripples in spacetime known as gravitational waves. Strong gravitational waves are released when two black holes merge, and these waves may be seen by specialist observatories such as the Laser Interferometer Gravitational Wave Observatory, LIGO. These discoveries give concrete proof of black hole collisions as well as important new information on the masses and distances of the involved objects. Over the last several decades, science has advanced significantly. In order to detect active black holes in a large number of galaxies, scientists have created novel algorithms in recent times. For example, Australian astronomers have modeled the radiation from galaxies and black holes at various wavelengths using an algorithm known as Prospect. They can now recognize the telltale signs of active black holes thanks to this approach, which also helps to explain their features and frequency in the cosmos. Scientists use a variety of techniques to investigate black holes in depth after they are discovered. They track the movement of gas and stars in the black hole's neighborhood to gain information about its mass and the gravitational pull it has on its surrounds. This contributes significantly to our understanding of the physical processes around black holes. Another method for studying black holes is reverberation mapping. By monitoring the temporal differences between emissions from several areas close to the black hole, this approach may be applied. Astronomers can decipher the mechanics of the accretion disk and the interaction between matter and radiation by examining these temporal delays, which allow them to sketch out the orbits of gas and photons around the black hole. That's not all, though. Additionally, state-of-the-art investigations like the Event Horizon Telescope (EHT) have completely changed our understanding of black holes. With the help of the EHT, a global network of radio telescopes, scientists can now take unprecedentedly high-resolution pictures of black holes. The EHT functions as a virtual telescope the size of Earth. The event horizon was visible thanks to the telescope network's successful imaging of the supermassive black hole at the galaxy's center, M87. It is one thing to be able to observe what scientists have been describing for decades, even though this was also known in the past. You would think that everything would be obvious now. That a black hole has been observed, right? However, it is where Brian Greene undermines all of that reasoning. His provocative theory suggests that the cosmos we live in is contained by a black hole. In actuality, this assertion arises from the complex interactions between black hole physics, quantum mechanics, and general relativity. Greene argues that fascinating possibilities arise when we apply the principles of general relativity, in particular, Einstein's theory of gravity, to the enormous size of the universe. Due to their strong gravitational attraction, black holes can cause major distortions to space and time in their surrounding areas. The fabric of spacetime becomes very twisted inside the event horizon of a black hole, where gravitational forces are at their highest, producing some really intriguing phenomena. According to Greene, the structure and expansion that we can see in the universe would be caused by gravitational forces operating inside a black hole. In this case, stuff falling into the black hole from outer areas would exert a gravitational pull that would cause the universe to expand. A possible explanation for the formation of stars, galaxies, and other celestial formations that scientists have been researching for decades is the gravitational collapse of matter. In fact, Greene's theory presents some very interesting options for solving some of the enduring riddles in contemporary physics. The fundamental incompatibility of general relativity and quantum mechanics is one of them. Quantum physics controls the behavior of particles at the subatomic scale, whereas general relativity effectively explains the action of gravity on a cosmic scale. It has long been a difficulty to combine these two theories into a single framework, sometimes called a theory of quantum gravity. Greene believes that the theory that we live within a black hole may offer a suitable framework for combining quantum physics and general relativity. It's possible that the enormous gravitational forces seen inside black holes might create a very special environment in which the fundamental principles of physics are altered. Furthermore, the idea of residing within a black hole may provide insight into the riddles of dark energy and dark matter. Even though these enigmatic elements comprise most of the matter and energy in the cosmos, little is known about them, including their nature and characteristics. Given that the characteristics and actions of the black hole itself may be responsible for the impacts of dark matter and dark energy on the cosmic scale, the idea that one is inside one might provide a possible explanation for their existence. However, if Greene's idea turns out to be true, it would completely re-evaluate the fundamental principles of physics and completely transform our present cosmological models. Although it is difficult to find direct observable data to confirm or deny this idea, there are some possible ways to assess its veracity. Finding observable signs that may distinguish between a world within a black hole and a cosmos that adheres to the conventional cosmological framework is one option. For example, some trends in the cosmic microwave background radiation, or remnant radiation from the early cosmos, may offer clues about the composition of the environment in our universe. An alternative strategy would be to do in-depth research into the behavior of particles at very high energy, such those generated in particle accelerators. Particles close to the intense gravitational forces within a black hole may behave in ways that are unique from what we now know about particle physics. Perhaps something is hiding in the details that we have been oblivious to all along. Thus, it would now be necessary to carry out theoretical studies using sophisticated mathematical models and simulations in order to investigate the effects of being within a black hole. These simulations may shed light on the physical rules, gravitational dynamics, and predicted observable signs that would be present in such an environment. If Greene's idea is indeed plausible, it might be verified by contrasting these predictions with observable evidence from astrophysical experiments or cosmological surveys. However, there are others who disagree with Brian Greene's theory, which contends that we live within a black hole, despite the fact that it is an exciting and thought-provoking idea. Several cosmologists and physicists present other viewpoints that completely refute Greene's theory. The concept of the multiverse provides one alternate perspective. According to the theory of the multiverse, there are many other worlds besides our own that exist. These realms are referred to as the multiverse. It's possible that every world in the multiverse has its own distinct set of physical constants, rules, and characteristics. This concept originates in several areas of theoretical physics, such as inflationary cosmology, quantum mechanics, and string theory. Proponents of the multiverse hypothesis contend that the presence of several worlds, each with unique attributes, might account for the wide range of physical laws and constants found in our universe. Basic factors including the intensity of gravity, the values of basic forces, particle masses, and even the number of dimensions might vary among these many worlds, sometimes known as pocket universes. According to this theory, the characteristics of our universe are only one conceivable arrangement among many that exist, neither exceptional nor unique. Maybe our world isn't the one within a black hole, but there could be other versions out there. The inflationary multiverse scenario, or endless inflation, is one specific multiverse idea. This theory states that the early universe had a phase of rapid expansion known as cosmic inflation, which produced new areas that eventually separated into universes with distinct physical characteristics. The speed of light. What prevents signals or information from traveling across these worlds, causing them to be causally separated from one another. One approach to answering the topic of how our universe is adjusted is through the multiverse hypothesis. The astounding accuracy of the underlying constants and physical rules that let life as we know it to exist is referred to as fine-tuning. Proponents of this hypothesis contend that if several universes exist, each with unique qualities, then it shouldn't come as a huge surprise if one of them has the ideal environment for life. According to this theory, the likelihood of discovering a world conducive to life is increased by the presence of a multiverse. However, you might also examine the complete opposite viewpoint. Perhaps the entire universe is a simulation. Over time, the hypothesis that our universe is a simulation of reality has drawn a lot of interest from philosophers and scientists alike. This theory holds that rather than being founded on physical rules and occurrences, our experience of reality, including our presence within a black hole, emerges from a virtual world constructed by highly evolved species or a higher intelligence. Proponents of the idea of simulated reality contend that observed phenomena, including gravity and the universe's structure, may be computer-generated models intended to replicate the features and actions of a black hole. From this angle, rather than being a genuine physical occurrence, Greene's sense of being within a black hole may be the product of programming or constraints in the underlying simulation. The quick development of virtual reality and computer simulation technology is a major source of inspiration for this point of view. It is not so implausible to envisage more evolved civilizations or creatures capable of simulating entire universes, especially as our own technical skills to create realistic simulations and immersive virtual worlds grow. The simulation hypothesis is further supported by a number of theoretical and philosophical considerations. For example, the simulation thesis put forth by philosopher Nick Bostrom implies that if technologically advanced civilizations exist, they probably have the capacity to produce lifelike simulations of conscious entities. It is statistically more likely, so the reasoning goes, that we are living in a simulation than in the actual world. Furthermore, observational constraints exist. Direct proof or observations from within a black hole are very difficult to get due to the strong gravitational attraction of the event horizon. Additionally, because of their nature, black holes are impervious to signals or information, making it challenging to explore their interiors and confirm if a universe exists there. That's not all, though. In addition, the theory calls into question the characteristics of space within a black hole and the meaning of time. There are difficulties in comprehending how our universe, with its rules of physics and structure, could persist under such conditions due to the high gravitational forces and curvature of spacetime near the singularity. The concept of a self-contained world within a black hole is complicated by the effects of time dilation and spacetime distortion. For the moment, however, let's set all of that aside and consider the possibility that we genuinely live within a black hole and that everything you believe to be true about the universe is untrue. One issue would naturally come to mind in this situation: if we are indeed within black holes, then how have we managed to gather such extensive information about other black holes during this time? Actually, there are a number of really interesting theories here. According to one hypothesis, the border of an area of space can encode all the information about it. This theory is based on the holographic principle. In this scenario, the universe may be a higher dimensional depiction of physical processes taking place on the edge of a black hole, or it may be a holographic projection. This would enable humans to see and study other black holes in our universe while continuing to live inside the black hole. The brain world theory, which postulates that our universe is a four-dimensional brain buried within a higher dimensional spacetime called the bulk, is another intriguing concept. This hypothesis states that black holes can originate in the bulk and in our universe, which would be the brain. Even if we live inside a black hole on the brain, we are nevertheless able to see and learn about other black holes that are part of the bulk dimensions. In fact, there are hypotheses that suggest that human capacity to live within black holes and conduct research on other black holes may be related to the phenomena of quantum entanglement. A phenomenon known as quantum entanglement occurs when two or more particles interact in a way that causes their states to instantly correspond, regardless of their distance from one another. It is proposed that humans might be able to study and learn about other black holes indirectly if there is entanglement between particles within and outside of a black hole that stretches over the event horizon. Perhaps Greene isn't speaking of impossibilities after all. Perhaps he is the only one who perceives this as the true reality, that we are in fact within a black hole and all current explanations are false. Do you agree with him? Let us know your thoughts in the comments below. If you like this video, please give it a thumbs up, and like always, we'll see you in the next one.